All right, so I have the pleasure of talking to you twice today. And this time is to introduce the activity for this afternoon, which is fitting JWST light curves. And I remember back in the original planning for this workshop, we were talking about what hands-on activities would be interesting, but also feasible. And we had a little bit of back and forth about whether it was realistic to actually fit JWST data or not. And in one meeting, I was like, we have to do this because this is like the most fun activity we could possibly do. It's such a special thing to be able to start all the way from the raw data and get to a spectrum for a planet at the end. So the title of this talk is fitting JWST data from light curves to planet spectra. I'm actually not going to talk so much specifically about JWST data, but rather about fitting light curves in general to give you the tools that you need to do the activity this afternoon. So as a recap, what hopefully worked for all of you yesterday is you worked through Eureka stages 3 and 4. So starting with a 2D image, summing it up to get a spectrum, and then taking that time series of spectra, dividing them into spectroscopic channels, and hopefully ending up with some beautiful light curves. And our task today is to start with these light curves, fit them with a model, and then fit each spectral channel individually so that at the end you can get either a thermal emission spectrum or a transmission spectrum. So the key things we want to know are how does either the planet to star radius ratio, so RP over R star, vary with wavelength, or the planet to star flux ratio, so FP over F star. Okay, so those were some nice cartoons. Light curve fitting is kind of an art. It is challenging. Historically, it's been even more challenging with JWST. It's a bit easier. Here is a particularly gnarly light curve from Spitzer. This is the same Spitzer phase curve of HD 1897333b that I showed in my talk earlier. And you can see here there's some astrophysical signals. So you can probably guess that this big feature in the middle, that's the transit. If you look carefully, you can see maybe an eclipse. You can ask yourself, can you see any thermal phase variation in there? Any evidence of a sinusoid? By my eye, definitely not. And then there's all of these, there's these wiggles, there's this slope. And so in practice, when we fit light curves, we simultaneously model that astrophysical signal and the instrument systematics. And don't worry, none of the examples we gave you today are as difficult as that. Okay, so starting with the astrophysical signal. So this is the same cartoon I showed earlier. Here are some of the basic features of a transiting exoplanet system. So you've got transits, you've got thermal phase variation. That's this sort of sinusoidal oscillation. And you also have secondary eclipses. And luckily, these effects can be modeled with analytic models. This is a bit of shameless advertisement for my own Python package, Batman, that I think many of you have used and will use today. And the parameters that go into these models are things like the size of the planet relative to the star, so RP over R star, or for an eclipse, instead you would fit the eclipse depth, often called FP over F star, so the flux from the planet divided by the flux from the star. Another key system parameter is the distance between the planet and the star. We typically express this in units of, well, this is dimensionless. So an A over R star value of 5 means that the planet is 5 stellar radii away from the star. Another parameter that's important is the orbital inclination. So you can imagine that if your planet is transiting, let's see. This is backwards. Oh, Nope. There we go. If your planet is transiting right in the center of the stellar disk, you'll get a longer duration transit than you would get if the planet is transiting down here, for example. Same thing with the orbital period. Longer period orbits mean the transit duration is longer. The transit time is important, so when the transit actually occurs. Orbital eccentricity also plays a role that affects the shape of the transit light curve, and also limb darkening. Just for calibration, raise your hand if limb darkening is something you have thought about or encountered in your own research. Okay, about half of you. Okay. If you have not encountered this, I'll briefly explain it here. So stars vary in their intensity depending on what region of the stellar disk you're looking at. And the reason for that is if you pretend you're the observer over here on the right-hand side, if you look at the center of the stellar disk, you have a totally perpendicular viewing geometry, so straight on here. And that means that for given optical depth, you can see deeper layers that are hotter than if you, say, look at closer to the limb, closer to the edge of the star, where that same optical depth puts you at a higher altitude in the stellar photosphere that's cooler. And so that's why stars look brighter in the center and fainter at the edges. And you can predict stellar limb darkening with models. I've listed Phoenix models and Creutz's models. Those are some of the commonly used ones. You can also fit for limb darkening parameters in the light curve directly, which can be really useful because often the models are not a perfect fit. And I'm emphasizing this because the transit depth and the limb darkening can be fairly degenerate. And so it's important to get this right. For example, particularly for M dwarfs that are cool enough that they have molecules in their photospheres, if you use an incorrect model of the limb darkening, you can produce a spurious water feature in the transmission spectrum of the planet. Here's some typical parameterizations for limb darkening. So a really common one is a linear law. Here's what these look like. So if you assume uniform limb darkening, or the disk of the star is the same brightness everywhere, you get this completely flat bottom transit. And the more precisely you want to resolve the shape of the transit, the more free parameters you can add to your limb darkening model. But the most commonly used ones are linear and quadratic. And that's also because those have analytic solutions, and so the models can be calculated really, really fast. Okay. There are also a number of different models you can choose for the phase variation. So the simplest one is a sinusoid, and that's actually the most commonly used. If you want to get really fancy, you can add a second sinusoid, or fancier still, you can fit spherical harmonics. And I can recommend the Starry package, which is incorporated in Eureka, that can do spherical harmonic models for phase curves directly. Okay, so those are all the astrophysical models. Does anyone have any questions about that before I move on? All right, that was the easy part. Systematics are the hard part. So I have some examples for you to illustrate some of the common types of instrument systematics that we've learned to expect from past work with Hubble and with Spitzer. So here's a famous one. Here's some raw Spitzer data on the right. I think those are eclipses. And there's all kinds of stuff going on here. So you see this initial ramp, very strong. And then here in the middle of the eclipse, you get this chopping pattern. The high frequency pattern is caused by Spitzer's intrapixel sensitivity variation. So the pointing of the telescope is not perfect. This is a map of where physically on the detector the center of the light is hitting. And that's compared to a model here of the sensitivity within a given Spitzer pixel. So as you move the center of light across the pixel, the sensitivity varies by a couple of percent. And if you combine this pointing variation with the sensitivity variation, you get these wiggly features here. And Kevin Stevenson in the front knows more about this than like any other human on the planet. Fortunately, JWST's pointing precision is much better, and so this is much less of an issue. Here's another classic example from HST, the STIS instrument. This is typical of HST data, where you can see there's actually big gaps in the data. That's caused by the telescope moving behind the Earth, so the Earth is in the way of the thing that you're trying to observe. So the data set is divided here into 4 different orbits of the telescope. And you can see that the shape of the transit is a little bit wobbly. And this is caused by warming and cooling of the telescope through its orbit. So when the Earth is in the way, it's cold. When it's in direct sunlight, it heats up. And so that causes slight changes in the focus of the telescope. We sometimes call this thermal breathing. And this can be fit with a fairly simple model. You can fit like a 3rd or 4th order polynomial and fit out this effect pretty well. This is a ground-based light curve. For the other cases, I gave a physical reason why they look the way they do. From the ground, it is anybody's guess. You know, the atmosphere is there, like Jason showed this morning. There's the fan causing the turbulence. We don't know. But what has emerged as the current state of the art solution to fitting, you know, whatever those weird wigglies are is to use a Gaussian process. And there's a number of packages available that can help you do that. All right, here's my last example. This is a really classic one. This is Hubble Wide Field Camera 3 data that also shows these exponential ramp features. The strongest one is happening here in the first orbit. You can also see it a little bit in the second orbit. And that's caused by charge trapping. So ideally in a perfect detector, if you have a photon that hits the detector, it's converted into some fixed number of photoelectrons that you can then read out. But in reality, some of the photoelectrons get trapped in the detector, so they're not read out. And it takes a while for those charge traps to saturate. And so that can produce these characteristic ramps that asymptote eventually to a constant value once all the charge traps have filled up. And it's possible to correct for this as well. The earliest models assume just a simple exponential function for the ramp. There are a couple other ways you can approach this, but it's possible to clean it up and get a remarkably precise light curve out at the end. This is data for GJ1214b. Okay. So putting it all together, the way you fit the light curve is you simultaneously model the physical signal. So for a hypothetical transit, you've got a transit model, which is a function of wavelength and also of time. You've got a systematic model, and here's a pretty typical one for Hubble. So you can see the features here. There's a constant. Ignore SFT, that's complicated. There's a quadratic term. So the linear term is V1, the quadratic is V2. And then there's also this exponential term for each orbit that's required to fit those ramps. And so all things considered, you might have, I don't know, 10 or 15 free parameters for each spectroscopic light curve. And typically what we would then do is calculate the best fit model with least squares, and then estimate the parameter uncertainties either with MCMC or nested sampling. Okay, so this is the most important part of this talk. How do I know if my fit is good? I think the fact that, you know, it is awesome that tools like Eureka exist. It makes it much easier and faster to do light curve fits than it ever was in the past. But it can be a little bit of a black box, and it's very powerful. So my message to you is that with great power comes great responsibility. And I'd like to go through a couple of considerations that you should think about to know whether your light curve fit is actually good or not. Okay, so how precise can your data possibly be? Not infinitely precise, and it's because of photon noise. So this is the fundamental limit in the precision of a light curve that you can measure. And this comes because in any time interval t, there's some very small probability that any hydrogen atom in the star is going to emit a photon. And if you remember from statistics, this is a little dry, but it's important. The sum of many low probability events is a Poisson process. That's where counting statistics come from. And so for any time interval, the expected for Poisson process, the mean number of photons is going to be n, and the noise, the uncertainty, goes as the square root of n. And you cannot do better than that. So there's always going to be root n photon noise, no matter how fancy your telescope is. Of course, there's also a lot of other sources of noise. I talked about some sources of noise from the detector. There's also stellar activity if you're observing from the ground. Earth's atmosphere is in the way. But the photon noise is the thing we should always be trying to reach. So how do you know if your fit is good? First question, did you reach the photon noise or not? And in practice, like actually reaching the photon noise is challenging. We don't always get all the way there. State-of-the-art space-based observations can often get within about 10 or 15% of the photon noise. From the ground, I've seen factors of a few over the photon noise. That's pretty good. You also want to check if your residuals from your best fit are normally distributed and whether they bend down as the square root of n as expected from the photon noise. So this plot on the right is called an Allen deviation plot. This is a super useful plot to check if your noise is behaving as it should. This is a nice example showing the RMS. So that's the root mean square deviation and the residuals. Bend in bins of this is 1 point per bin, 10, 100, 1,000. And the red line is the root n predicted decrease in scatter as you bend down for photon noise. And the data are shown in black. And so this is a perfect example of the data bending down is exactly as you would expect for photon limited statistics. Okay, so here's an example. Do you think this fit is good? If you think it's good, raise your hand. Got some hands up? Lots of hands up. If you think it's bad, raise your hand. Oh, we have a couple. So, whoop, I gave it away. No. Folks who thought it was bad, why do you think it's bad? Could be. It depends on how bright the star is. So if you have a really bright star, big telescope, that number will be smaller. There were some other hands up. Yeah. There's a small bump. Where is it? In the, oh, here. Little bump. Okay. This is really tricky because the human brain is exceptionally good at looking for patterns. And so very, very often I look at residuals, I'm like, oh, there's totally a bump there. In this case, I think actually not. So one of the things you can use as a sanity check is you can just take a histogram of your residuals. It should be perfectly Gaussian. This full disclosure, this histogram isn't actually from these data, but I thought it was a nice histogram. So this is for illustrative purposes only. But one of the other things you can do, like if you're like looking at a paper and you're like, is this a good fit or not? You can just do we call the 65, 95, 99, 7 rule, which comes from Gaussian statistics. And all that says is that about 68% of your data points should be within 1 sigma of the mean. 95 of them should be within 2 sigma, and only 0.3% should be outside of 3 sigma. And so I shaded here the 1, 2, and 3 sigma contours, and it actually works out pretty well. So there's, I think, about 100 data points here, and there's 2 that are between 2 and 3 sigma. So that's pretty close to what you would expect for Gaussian statistics. Okay. What about this one? Is this one good? Raise your hand if you think it's good. See a few hands. Raise your hand if you think it has some problems. Okay. All right. Who would like to volunteer a problem that you see in the back? Yeah. What's that? Look at that. Anything else? Yeah. Yeah. Yeah, here. What the heck is that? And full disclosure, I reduced these data, so I'm allowed to be critical. This is, this is tricky. Like, this is a bright star observed from space, and so the photon noise is really small. And we did our best with this light curve fit, but there's still some weird stuff that we couldn't explain. Yeah, so noticeable correlated noise, more outliers than you would expect for Gaussian noise. So what do? Panic. No, that's not true. There are things that you can do. What you cannot do is ignore it. So you have to account for this in your fits. And fortunately, there are several ways to do it. So the first thing that I would recommend is, if your light curve fit doesn't look awesome, think about what additional free parameters you might want to include that could help fit the data better. Here is an example of a data set that has a little bit of excess red noise here on a time scale of maybe 20 to 30 exposures. You can see it if you look at the residuals. So you can see here, these points are clustered a bit high. And then there's maybe a bit of a quadratic structure here. If you kind of squint at it, you can see it, right? And now you want to be careful, because you can't keep adding free parameters forever. You end up overfitting. You want them to be physically motivated. But in this case, here's an example where if you add the signature of the phase variation of the planet, or I should have said this is a secondary eclipse. And so here, the hot day side of the planet is rotating into view. Planet goes behind the star, and the day side rotates out of view. And that fixes your problem. So this tiny little excess of red noise that you see here is corrected down in this bottom example. Good job to Sebastian for spotting that in like 5 minutes after reducing the data. Where are you, Sebastian? Yeah. Nicely done. All right. So what happens if you don't have evidence for correlated noise, but your RMS, your scatter, is still bigger than expected compared to the photon limit? In that case, a very common thing you can do is to rescale the error bars. So to illustrate this, I just did a toy model. I said, pretend that the underlying signal is just a line, y equals mx plus b. And I modeled some points based on that line. And you can see that there's a bunch of scatter here. So these are underestimated error bars. If you calculate the reduced chi-squared, typical statistic to measure goodness of fit, it comes out to be about 5, and it should be close to 1. And so a very common approach is to just rescale the error bars by a constant factor, the square root of the reduced chi-squared, so that you reach a reduced chi-squared equal to 1. And so you can see for the same data, these error bars have been increased by a factor of almost 3, and all of a sudden the fit looks a lot more reasonable. Now, I should say as a caveat, this only applies when the underlying noise is uncorrelated in time. So you have to have Gaussian distributed noise for this to apply. If you have red noise, as I said earlier, the most common approach these days is to use a Gaussian process. That is well beyond the scope of this talk. We could talk about Gaussian processes for an hour. I'm not going to do that. They're incorporated into Eureka, though, and so if you want, you could try them out this afternoon. I also want to mention an old school approach from Frédéric Pont from 2006 that is useful if you want to get a rough idea of how much the red noise might be affecting your uncertainties. And the idea here is you just compare the you look at the time scale of the transit or ingress and egress, and you see how much larger the residuals are there compared to what was expected from the photon noise. And that's a rough scaling factor for the uncertainty on your model parameters. Okay, so I'm almost done. This is not part of the exercise this afternoon, but if you're fitting light curves for real, you want to be really careful about how you estimate the uncertainties on the fit parameters. And so 4 points to think about. First, if you are doing an MCMC or nested sampling, make sure that the uncertainties on the data points are legit. Because if you have underestimated uncertainties on your data points, you're going to have underestimated uncertainties on your model parameters. Once you're satisfied of that, then often we'd make an initial guess with the least squares fit. Then use some kind of sampling approach. So either MCMC or nested sampling with something like Dynasty. These are both common approaches these days. And then finally, you also want to make extremely sure that your sampler is all the way converged. And this is also another topic that we could talk about for like an hour. I'm not going to talk about it now, but I wanted to note it here for completeness. Okay, so now that you have done all of this hard work, you are satisfied that your light curve fit has reached the photon noise limit. You've accounted for all the astrophysical signals, all the instrument systematic effects. If you can't actually reach the photon noise, you've done something to account for that. You don't just pretend everything is fine. Your parameter estimation is converged. Then you're allowed to look at the transmission spectrum or the emission spectrum. Don't look at it before you're confident that your model fits are good, because you're going to see all kinds of weird stuff and convince yourself that things are there and bias your expectations. It's better to do a good job on the fits first and then open the lid and see what you get. Okay, that's everything I have to say. So I'm leaving you with a checklist of a couple of important points to think about. Have fun fitting the light curves. And I think before we turn you loose on the data, Taylor had a few final comments.
Do you want to take questions?
Oh, yeah, sure. Oh, yeah, good. Okay. I'll take questions and then I'll hand it over to Taylor.
Thanks for that talk. That was really helpful to see. So speaking of getting the transmission spectrum out of all of these light curves, so when you work with JWST data, you might have like hundreds of thousands of spectroscopic light curves. And it's good to see how you can like visually inspect if your fits are good. But if you want to do that for like hundreds of thousands of light curves, that might be challenging. And especially if you want to like convince a referee that all of your light curve fits, which you get the transmission spectrum out of, makes sense. it might be helpful to have like a more synoptic way of approaching that. So do you have any recommendations of how to check many light curves at a time if all of these seem to do good? Or
Yeah, that's a really good point. And that's something that hasn't come up in the past because we just didn't have that many spectral channels. Does Kevin have a comment?
So one of the tools you can use is the scatter multiplier factor. This increases the size of the error bars so that you reduce chi-squared as 1. At the stage 6, we plot that out as a function of wavelength. And so you can see how well you're doing for each of your spectroscopic channels. And it should be fairly smooth, right? You might be within 10% of the photon limit for a vast region of your wavelength spots range. And then maybe at the edges, it gets up to 1.5 or 2. If you have huge outliers, it'd be visually very easy for you to hone in on that particular spectroscopic channel and say, yes, that something's going wrong there. Let me go look at that one in more detail.
but as Laura said, the just inflating the error bars like that only makes sense when the error bars are distributed in a Gaussian way, I guess. So this would not be a way to identify correlated noise in any of the spectroscopic light curves, correct? Okay.
Yeah, I would like as a rule of thumb, I would recommend just doing big bins to start to get kind of a sanity check of what they look like. Usually the smaller the bins are, the higher the photon noise is. So these effects, like if you're doing okay with big bins, making the bins smaller is generally okay, although not always. So yeah, but I think, you know, it really pays off just to look at these things. Like even if you're paging through 100 Allen deviation plots, like that's 5 minutes that's really worth your time.
Okay, thank you.
This one in the front from Taylor.
I'll ask one of the questions that was posed online. When talking about limb darkening, you said that limb darkening coefficients can be degenerate with transit. So the question is, what does degenerate mean? And adding to that, how do you know if something's degenerate? Do you panic? What can you try and do?
You definitely panic. No, no. So basically, the limb darkening makes the star fainter, and the transit also makes the star fainter. The way you can tell the difference is that they the shape of the transit depends on whether it's the planet that you're seeing or whether it's the stellar limb, because the effect at the limb of the star so close to ingress and egress is much stronger than in the center of the transit. So the way you tell if things are correlated is by looking at results from an MCMC or nested sampling. You look at the posterior distribution of the parameters. And if they're completely uncorrelated, it'll look like a circle. If the parameters are correlated, you'll see more of a hot dog shape. And that's okay. If the parameters are correlated, that's normal. That happens a lot. And if your sampler is converged, those correlations will be accounted for in the amplitude of the error bars. I think everybody's ready to fit the data. Okay. Hand it over to Taylor.
Yeah. So yesterday I kind of just let you figure things out on your own for the workshop number 1. Today, some of you will have worked on workshop number 1, some of you will not have, and so to help people who didn't participate yesterday but want to participate today, or who tried to participate yesterday and had a really hard time, we've made available inputs to workshop number 2 that don't require you to use your own results. So yeah, that's an option available to everyone. If you feel confident in the results you got yesterday, you can try using your own results. But you do so at your own risk. If we have however many 100 people we have and another number online, if everyone's trying their own results and they're all like, I don't know, I can't get a good result, and it's because you're running your own data, we can't help you get all the way through all the stages. We will be releasing kind of a solution manual to each of these notebooks eventually. And so, yeah, don't feel like, oh, you have to be able to do it all on your own. I would recommend, yeah, using the provided inputs to workshop number 2. And so yesterday, I told you to download some stuff to get ready for workshop number 1. Anyone who didn't do that should make sure to go to the Sagan Summer Workshop website, go to the hands-on sessions page, and then there's a before the workshop area, and there's some PDFs there that tell you how to get started on Google Colab or on Jupyter Notebook. For workshop number 2, because it's so very tightly thematically linked with workshop number 1, we paired all of those inputs for workshop 1 and 2 together. So if you attended yesterday, there's nothing new to download. All of the files you need are already in your Google Drive. But please really carefully read the instructions, because if you don't, then by accident, you will end up using your own results, or you'll use some results that you ran at the end of the day, just playing around, having fun, that didn't get you good results. And so, yeah, Eureka allows you to choose which exact folder you want to use as your input. If you ran 15 different choices yesterday and you like number 5, you can tell Eureka, use number 5. So yeah, just really, really carefully read the instructions, and yeah, have fun. We have helpers here. Can the helpers put their hands up again? So yeah, everyone look around. Ask your friendly neighborhood helper. There's helpers online as well. And for the people that are online only, I'd ask that you pose your questions in the Slack, because I can check Slack on my phone while walking around helping people out in person, and trying to monitor Zoom and Slack at the same time is just not possible. So yeah, in-person people, online people, feel free to ask things on Slack or raise your hand, or yeah, ask people around you. And yeah, have fun.